9.6, solving rational equations. We want to understand in this first example that we need to factor those denominators. Anytime you want to solve an equation, we've got to get the denominators to be the same. And keep in mind that when we get done with these problems, we're going to have to check the solutions for extraneous solutions because they might exist. So we want to check for those. Don't think that we're not going to have those as possible problems to deal with. So, first I look for a GCFs. That's always the first thing I want to do in factoring. So I can take the 2 out. And I don't see a GCF over here. However, I do see that it is a difference of perfect squares. So I have x plus 1 and x minus 1. So next, what I want to do is I want to multiply, find my common denominators, and ask myself the question, what is one denominator missing that the other one has? Well, clearly this denominator over here is missing an x plus 1. So I'm going to multiply the top and the bottom by x plus 1. And what is this denominator missing that the other one has? It's definitely missing a 2. So I'm going to multiply top and bottom by 2. So what we have here is 5x plus 5. That's if I distribute the 5 to that x plus 1 over the 2, the x plus 1, the x minus 1. And 30 over 2 times x plus 1 times x minus 1. Now, clearly I can see that if we would possibly come up with 1 or negative 1, those would not be good solutions. Why? Because they cause the denominator to become 0. So I definitely know that x cannot equal positive or negative 1. Now that might not be the only extraneous solutions, but I definitely know those would definitely be problems or things that I could rule out. Okay, so what happens when you look at these two equations, what happens if you multiply everything by that common denominator? Well, as we've talked about in section 9.5, if you get all the denominators to be the same on both sides of the equation and you'll multiply through by it, and I don't have enough room, otherwise I'd write it over here, that denominator is going to cancel out. So really we're dealing with 5x plus 5 equals 30. And then we can subtract the 5 and get 25. And we can divide by 5 and get x equals 5. Now that's the only possible answer. So possible, remember how we would do possible and extraneous and actual solutions. Well, the only possible solution is a 5. Well, plug it back into the original equation and see if it works. So come back up here to the top. We've got 5 over 2 times 5 minus 2. And we got 15 over 5 squared minus 1. Well, 10 minus 2 is 8, so that's 5 over 8. And here we have 25 minus 1 is 24, so that's 15 over 24. Now those happen to be the same fractions, 5 over 8, 15 over 24, so I know we have a good solution. If you need to cross multiply to double check that in your own mind, then you do it. Go ahead, 8 times 15, 5 times 24. I'm sure you'll get 120 for each one. So, in other words, there are no extraneous solutions, but 5 is the actual solution. And I want to make sure that I note that in my possible, extraneous, and actual solutions. So let's try it again. Let's do a different problem. So, looks like both of my denominators are factored. That's even nicer than the problem before. What is this denominator missing that the other one has? It's missing a 5. So I'm going to multiply top and bottom by 5. So what did we say about those denominators? When you multiply everything through by 5 times x plus 2, bingo, bango, bongo, they're all gone. I got negative 4 equals 15. Uh-oh. That's never going to happen. So there's no solution in this situation. There's nothing in the universe which is going to make 15 equal negative 4. So if you end up with a situation like that, there's no way to solve that. So let's try again. Let's try on a different problem here. Factor the denominators. Uh-oh, I thought I could factor that. Well, I guess that is a factor. X squared minus 2. I can't factor that either. So what's this denominator missing that the other one has? It's missing an x minus 4. And what's this denominator missing? It's missing an x squared minus 2. Now I know some of you are saying, well, why can't you factor that x squared minus 2? Well, it's not a difference of perfect squares. 2 is not a perfect square, so I can't factor it. And if I multiply everything through by the common denominator, gone. So, distributing this, we get negative 2x plus 8 equals 2x squared minus 4. Well, that gives me, oh, I see a quadratic term and a linear term. So I end up with 2x squared. If I push these things to this side, I get plus 2x minus 4, and a minus 8 would make minus 12. So 2x squared plus 2x minus 12. We can factor out a 2, giving us x squared plus 1x minus 6 equals 0. Continue to factor this. You've got an x and an x, plus 3 and minus 2, plus 3 and a minus 2. So in terms of your possible solutions, right, you've got your possible solutions, your extraneous, and your actual solutions. Negative 3 and positive 2 are possible solutions. Negative 3 and positive 2. So let's see what happens. Go back up to the original problem. Let's try plugging in the negative 3. So we got a negative 2, we got a 9 minus 2 on the bottom, so that's negative 2 over 7 and 2 over negative 7. Whoop, those are the same thing. So negative 3 is a good solution, so I'm going to write that down on my actual solution line. I know that you can't see that on screen right now, but I wrote it down, and I'll show it to you in a minute. I'm running out of room here, so I'm going to have to go to a different spot to do this one. Let's see here. Plugging in the positive 2, I've got negative 2 over 2 squared minus 2 equals 2 over 2 minus 4. So that's a negative 2. 4 minus 2 is 2. And then I've got 2 over negative 2. Hey, that works out. Both sides are equal to negative 1. So 2 is a good solution. This also does not have any extraneous solutions. Okay, let's try another example here. Looks like all my denominators are factored, which is nice. So I need to ask myself, what's this denominator missing that the other ones have? It looks like I'm missing a 5. What's this denominator missing? It's missing a 2. And this one's missing a 5 and an x. So make sure we multiply. So now we have denominators of 10x. And here I have 5 minus 4. And 5 minus 4 is 1. And on the other side I have 5x. And if you multiply everything by the common denominator, we know that that disappears on us. So we have 1 equals 5x. So x would be equal to 1/5. X equals 1/5. All right, so if x is equal to 1/5, we can, that's our possible answer is 1/5. So we need to check and see if it's an extraneous solution or an actual solution. Okay, let's plug it back into the original statement. We had 1 over 2 times 1/5 minus 2 over 5 times 1/5 equals 1/2. Alright, so let's see here. That would be 1 divided by 2/5 minus 2 over 1, right? 5 times 1/5 is equal to 1. 1 divided by 2/5, well, that's really, we're talking about the reciprocal of 2/5, which is 5/2 minus 2. Well, we know that 5/2 is equal to 2.5, and if we take away 2, we do get 1/2, so that's good. So 1/5 is an actual solution. We do not have any extraneous solutions in this case. Okay, check again here. Let's see, what's our common denominator? Well, we've got an x here and an x plus 1. As I've talked about in class before, please do not think that you can just simply put plus 1 to the numerator and denominator over here. That is not going to cut it, and if you do that, you're going to lose a bunch of credit, because that is completely wrong. In fact, you probably lose all the credit. We are missing an x plus 1 to the top and an x plus 1 to the bottom. We are also missing over on this one, we are missing an x. Here, we're missing an x and an x plus 1. X and an x plus 1. If we multiply through by all those denominators, we can eliminate them, as I've shown you in several other examples. So we have 4x plus 4 minus 3x. Please make sure that the minus sign goes with that set of terms, equal to x squared plus x when I distribute this. So it looks like I have a couple terms I can combine together, and definitely going to throw everything to one side, setting it equal to 0. So we have x squared. We have an x. Okay, these together create 1x. So when I subtract 1x from both sides, I end up eliminating my x's, right? 4x minus 3x. Those things get taken to that side, and that gets rid of that x. So we're just left with x squared. And then the minus 4. Of course, then I can factor that into x plus 2 and x minus 2. Giving me two possible solutions, positive and negative 2. Now, do any of them cause me any problems? Well, let's take a look. Let's throw in our throw them back into the original problem. Whoa! Sorry, folks. Had a little bit of a NASCAR wreck with a math book, but it seems like we're back. When you plug these back in, you're going to find out, as I've done in several other problems, that they both work. I'm running out of room here, so I'll just go ahead and cut to the chase on that. If you plug them back in, you're going to find out that both solutions work and are actual solutions. Your least favorite part of this section is going to be the story problems, so we really need to focus a little bit of attention on those. you're really going to be boiling this down into two different types of situations. Um, adding expressions to get a total, or the second situation, setting two different expressions equal to each other. That's really what's going to happen here. Now, the two formulas you're probably going to work with a lot are distance equals rate times time, and work equals rate times time. So we got distance equals rate times time, and work equals rate times time. Those are the two formulas you're really dealing with. Okay? In our first example, example 3, we're talking about this aerodynamic covering on this bicycle increases a cyclist's average speed by 10 miles an hour. Okay? The time for a 75-mile trip, so we automatically know that whether we're riding without the covering or with the covering on this this cyclist or this bicycle, we know we're going to be traveling 75 miles. But it says that it's reduced by 2 hours. Well, I don't know what the covering is without, or the time is without the covering. But I do know that when I add the covering, that I take off 2 hours of time. So that's obviously impacting the speed. Now, here's the part that a lot of you get confused about. It wants to know what the average speed for the trip is using the aerodynamic covering. But it never gives me any information about the rate. What I want you to realize is that two of these columns will be variables or expressions with variables. Two of these columns in these types of problems, because we're going to have expressions. So how do I connect distance and time to come up with rate? Well, honestly, you are going to be modifying the equation distance equals rate times time. You're going to be modifying it to rate equals distance over time. So if I were to write these using the distance there and the time t there, even though it's a variable, I get an expression which represents the rate. No, it's not a number yet. I understand that. Same thing here. 75 over t minus 2. Well, so the question said that the average speed, or it said that it was increased by 10 when you use the covering. So the rate without the cover plus 10 miles an hour is equal to the same rate with the cover. Now, we know that 10 has a denominator of 1, so we can start asking ourselves, what is this denominator missing? Oh, it's missing a t minus 2, so we'll multiply the top by t minus 2. What's this denominator missing? Oh, it's missing a t and a t minus 2. Sorry, I didn't give myself enough room here. What's this denominator missing? Oh, it's missing a t. So if we distribute that 75, we get 75t minus 150 plus 10t squared minus 20t equals 75t. Now hopefully at this point, because of all the problems that we've been working on, you can understand that I'm not just I am multiplying everything by the common denominator. Therefore, that's why all those denominators pretty much just get wiped out. Okay? So, if I combine everything together, I got 10t squared. I've got 75t. Take away 20t. That's positive 55t. I'm going to bring this 75t over, so that's a minus 75t. And then I have a minus 150 equals 0. So 10t squared minus 20t minus 150 equals 0. I see a common factor of 10 that I can pull out. And then I can continue to factor that, breaking up the set of parentheses. right? T minus 5t plus 3. So time could be 5 hours or negative 3 hours. I don't think it's going to be negative 3. The time it's going to take without the covering is 5 hours. The time it took with the covering is 3 hours. So what does it say? What's the question? What is the average speed for the trip using the aerodynamic covering? So 75 divided by 3 is 25 miles per hour. Okay. Now, there's a check understanding question on check understanding number 3 on page 513. Same type of problem. Since I have space in a different spot here, let's see what's happening in this particular. It says Rosa can jog 5 miles downhill. So downhill, her distance is 5 miles. In the same time. Oh, in the same time. That's going to be an important thing because this is not adding two things together. This is setting two things equal to each other. This is that second situation we were talking about. In the same time. So we'll be setting two times equal to each other. It takes her to jog 3 miles uphill. She jogs downhill 4 miles an hour faster than she jogs uphill. I do not know how fast. I do not know how fast she jogs uphill, but I do know that she jogs 4 miles an hour faster when she's going downhill. And they want me to find out the jogging speed each way. Well, if distance equals rate times time, then we could write rate equals distance over time, or we could write time equals distance over rate. This is the one we're going to be using in this particular example. So distance is 5, rate is x plus 4. Distance is 3, rate is x. Sorry for the scribble. It said that we were talking about the same time, so these two times are going to be set equal to each other. So 5 over x plus 4 equals 3 over x. So common denominators, please don't add the plus 4, do that illegal trick. Please make sure that you're looking at the factors. X plus 4 to the numerator and denominator. This one is missing an x, obviously. When you multiply through by those common denominators, obviously you lose the denominators. So we have 5x equals 3x plus 12. And simply solving it, we subtract the 3x, giving us 2x equals 12. So x is 6. So now we know the rate going uphill, and obviously the rate going downhill is 4 units faster. So those are the rates for uphill and downhill. Okay. Example 4 is another adding rate situation, but it involves a amount of work, in this case stuffing envelopes. And they talk about Tim can stuff envelopes 3 times as fast as his daughter. Okay, I have no idea how fast or how much time it takes Tim to stuff the envelopes. But I know that if Georgia was doing it by herself, it would take her 3 times as long. And it says that they have to stuff 5,000 envelopes. So if you needed another column for work, like we had distance in the last one, it would contain 5,000 in every single column, in every single entry, because that's the amount of work that's being done. But it says that working together, Tim and Georgia can complete the job in 4 hours. So they have a combined time of 4 hours. Now, work is rate times time, just like distance. And so rate is equal to the work over the time. Well, the number of envelopes is 5,000. And if Tim was doing it by himself, his rate would be 5,000 divided by his time, which is x. If Georgia was doing it by herself, it would be 5,000 over 3x. Together, it's 5,000 divided by 4 hours, or 1,250 envelopes. So together means that I'm going to be adding these things up. So we have one rate, 5,000 over x. We have another rate, 5,000 over 3x. And lastly, we have the total combined rate of 1250. We know that's over 1. So, getting a common denominator, this one's missing a 3, so I'm going to multiply top and bottom by 3. And this one's missing a 3x, so we'll multiply top and bottom by 3x. And then, of course, we can ignore those denominators because they're all the same. So we have 15,000, whoops, put my comma in the wrong spot, plus 5,000 equals, what do we got there? 3750 x. So that's 20,000 equals 3750 x. So x must be, drum roll please, 20,000 divided by 3,750 gives me 5 1/3 hours. That would be 5 hours and 20 minutes for those of you who want to know to the exact minute. But that's their combined. Okay, so we just figured out that it would take Tim 5 hours and 20 minutes to do all the work on his own. It would take Georgia, if I take 5.3 repeating times 3, it would take her 16 hours to do it all on her own. So 5 hours, 20 minutes for Dad and 16 hours for the daughter, just if they're doing it on their own. All right, my last example is check understanding 4a on page 514. It is another type of situation like we were doing before. This time it says, suppose Maria can stuff envelopes twice as fast as her friend Paco. So Maria can do it twice as fast. Her rate is twice as much as Paco's rate. I do not know what Paco's rate is. It does say that together they can stuff envelopes in 4.5 hours. 4.5 hours. So their combined time is 4.5 hours. Obviously, their combined rate would be 2x plus 1x. The time, for instance, so let's see here. We've got 6,750 and work equals rate times time means that time is equal to work divided by rate. So if I take this 6,750 and divide by 2x, I get the time that Maria could do it on her own. And the 6,750 divided by Paco's rate. And then if I add those two things together, I'm going to get 4.5. So 6,750 over 2x plus 6,750 over 1x equals 4.5. This is a time. This is a time, and when I add those two times together, I get 4.5. So I can see this is clearly missing a 2, so I'm going to multiply the top and bottom of that by 2. This denominator, which is a 1, is missing a 2x, and so I'm going to multiply the top by 2x. So obviously, if I multiply by all those denominators by 2x, I would eliminate those, giving me 6,750 plus 6,750 times 2, that's 13,500, equals 9x. Alright, so let's see here. 6,750 plus 13,000 gives me 20,250. Dividing that by 9, I will find out that x is 2,250. So in other words, Paco's rate is 2,250 envelopes per hour, and Maria's rate is twice that. She can do 4,500 envelopes per hour. Now it says, how long would it take each of them working alone? Okay, well, for Paco, 6750 divided by 2250, that's as if he's working it all by himself. It would take him 3 hours. And obviously for Maria, 6750 divided by her rate of 4,500 envelopes an hour makes 1.5 hours. So those are the times for the two individuals. Make sure you write all your questions down. You have circled or identified everything in the notes that you want to go over with me in class, and we will talk about those tomorrow.